Have you ever just looked at a simple metal part, like a bracket or a click, and really wondered how it's made? Not just one of them, but millions, and every single one is a perfect copy. Well, let me tell you, the process behind it is way more incredible than you'd probably guess. All right, let's get into it. I mean, just look at these. They're literally everywhere. Inside your phone, all over your car, holding your kitchen gadgets together. They seem so simple, almost forgettable, right? But what if I told you that making these things with absolute precision, millions and millions of times, is actually one of the biggest challenges in modern manufacturing? So how on earth is it done? The secret is a method that turns plain metal into finished parts at an insane speed. So what is this big secret? Well, think of it like a whole assembly line, just squished down into a single, unbelievably powerful machine. It's called progressive die stamping. Okay, picture this. You have this long ribbon of metal feeding off a huge coil, and it's sliding through this incredibly complex tool called a die. Now, with every single massive thump of the press, a whole bunch of different things happen at once. A hole gets pierced here, a feature gets formed there, a bend is made further down the line. A totally finished part literally pops out at the end with every single cycle. It's this beautiful, high-speed symphony of engineering. So how do engineers even begin to choreograph this crazy, high-speed dance of metal and force? Well, it all boils down to one thing: a master plan that controls the entire process. And this quote right here, it just says it all, doesn't it? The strip layout, it's not just some drawing. It is the absolute roadmap for the whole project. It determines the cost, the quality, even the speed of manufacturing. If you mess this up, the entire multi-million-dollar operation could completely fall apart. No pressure, right? And this slide just breaks it down perfectly. On the left, that's a real-world strip layout. You can see how intricate it is. Every single step is planned out. But then on the right, you can see how all that complexity really boils down to just a few key ideas that every single designer has to get right. These three terms, they're the absolute bedrock of the design. The pitch, that sets the whole rhythm of the machine. If it's off by even a tiny fraction, every single operation down the line will be a disaster. The bridge, well, that looks like wasted metal, but it's actually the crucial skeleton that holds the whole strip together while it's getting slammed and bent. And the strip width? That one's the starting point for the biggest challenge of all, which is cost. So why are they so obsessed with that layout, with how the parts are arranged on the strip? It's because of this number, a mind-boggling 75%, sometimes even more, of the total cost of one of these parts is just the metal itself. Every tiny sliver of material you waste adds up to a fortune when you're making millions of them. And this just puts it all into perspective. If your design wastes just 10 grams of metal per part, that's about the weight of 2 nickels. Nothing, right? You could be throwing away 1 ton of perfectly good material in a single 8-hour shift. The tiny optimizations they make at the very beginning, at the design stage, that's everything. But the layout isn't just about saving cash. It's also about physics. You can't just take super strong metal and bend it and cut it however you want. To keep things from going horribly wrong, engineers have to follow a really strict set of rules. Which leads to a really fundamental question. I mean, it sounds simple, but how do you take a piece of strong metal and put a sharp bend in it without it just cracking and falling apart? The answer is hidden in the metal's invisible structure. Just like a piece of wood has a grain, rolled sheet metal does too. If you try to bend the metal with the grain, it's weak. It's going to crack. So the trick is to orient the part on that metal strip so that all the important bends go against the grain. That one little decision is what makes the final part strong and reliable. Here's another classic problem. When you bend metal, the forces involved are just immense. So if you make that bend too close to a hole, like you see on the left, all that force has nowhere to go and it just deforms the hole. But by following the rules and just adding a little bit of space, the hole stays perfectly round. Every time. And there are so many of these rules. Engineers have this whole playbook with formulas that are all based on the material's thickness, which they just call T. For example, any hole you punch has to be at least 1.2 times the thickness of the metal. Otherwise, the tool itself might just snap. And the distance from a hole to the edge needs to be at least 2 times the thickness to stop it from bulging out. It's this intense level of precision that keeps things from going wrong in the first place.
But what happens when those rules get broken? Or when something totally unexpected happens during this super high-speed process?
Well, you get a whole menu of potential disasters. We're talking about ugly wrinkles and cracks that just kill the part's strength, or edges that don't line up, which makes assembly impossible. Any one of these defects can create literal mountains of scrap metal and bring a multi-million-dollar production line to a screeching halt. But even if your design is perfect, stuff can still go wrong. And the most common enemy, the biggest headache, is the burr. See that tiny, razor-sharp little ridge on the edge of the part? That's usually caused by something as simple as a cutting tool getting a little bit dull or the gap between the punch and the die being off by just a hair. These tiny flaws are a huge problem and require expensive extra steps just to file them off. So with all of this on the line, how do modern manufacturers possibly guarantee success and avoid all these expensive problems? Well, they don't wait for things to go wrong. They figure out how to solve problems before they even exist. Now sure, you've got these incredible high-tech machines that can scan finished parts for flaws. But, checking for mistakes after you've already made them isn't very efficient, is it? The real revolution is stopping those errors from ever happening on the factory floor to begin with. And they do this with some seriously game-changing technology. Instead of doing expensive, slow tests with real steel and a real press, they use what's called a virtual tryout press. It's basically powerful software that lets them solve all these problems before they become real problems. So here's how it works. First, engineers build a perfect digital twin of the part and all the tooling inside the computer. Then, they hit a button and run the entire stamping process virtually. The software simulates all the insane forces at play, and it predicts exactly where that metal is going to crack or wrinkle or even spring back out of shape. This lets them find and fix every single potential problem in the design before a single piece of actual steel ever gets touched. It's an absolute game changer. It saves weeks of time and just tons and tons of money. So the next time you pick up some gadget and see a simple little metal bracket inside, just remember the hidden world that's behind it. A world of high-stakes planning, material physics, and incredible virtual testing that perfects that little part before it ever becomes real. It really makes you wonder, doesn't it? What other simple things around you right now are actually masterpieces of hidden engineering?